Okay, so this next chapter is on chapter 4. This is about covalent bonds and molecules. We've talked about this from chapter 3, just the difference between them, but a covalent bond is one that results from sharing electrons between atoms, and those types of compounds we refer to as molecules. Some physical properties. How that bond forms, we know that there are attractive forces between the nucleus of one atom and the electron of another, and there are repulsive forces between the electrons of each of those atoms too. So it's a combination of this attractive and repulsive forces that gives a net attractive force that helps to bind those atoms together. There's an optimal distance that the atoms need to be in proximity to each other. You can see here from this chart that if they're too close, then there'll be too many repulsions and those two hydrogen atoms would not stay together. On the flip side, if those atoms are too far apart, then the attractions are too weak and then no bonding occurs. So there's an ultimate length where the bond does occur. That's referred to as the bond length. You can see here bond length for H2 is 74 picometers. The bond lengths would differ for different atoms. Just in terms of, I don't think this is in the slides, but just in terms of lengths and multiple bonds, so you can talk about single bonds or double bonds or triple bonds. Single bonds are of any two identical atoms, let's say nitrogen. So a nitrogen-nitrogen single bond would be longer than a nitrogen-nitrogen double bond, and then the double bond would be longer than the nitrogen-nitrogen triple bond, because essentially the triple bond is holding, there's more electrons holding those two atoms together than you see in the double bond than you see in the single bond. In terms of bond energy, this comes by a little bit later, but in terms of bond energy, a single bond is the least amount of energy. A double bond is stronger than a single bond, but not doubly strong. And a triple bond is stronger than a double bond, but again, not triple the strength of a single bond. And then lastly, the other thing you'll see referred to is something called bond order. This just refers to the number of bonds between two atoms. So a single bond is said to be a bond order of 1, a double bond is a bond order of 2, and a triple bond is a bond order of 3. So again, I know that's not really on a slide here, but it is important information from this chapter. Here's a table of average bond dissociation energies. It would be the amount of energy. You can think about it in two ways. This is the amount of energy that would be needed to break apart these atoms, and that's why it's called the bond dissociation energy. It's also in the reverse, the amount of energy that is released when the bonds form. And when we talk about thermochemistry, we'll use these to actually calculate energies of reactions. Those are my chickens in the background. Hopefully they're not too much of a distraction for you. So the other thing to note about covalent bonds, because those electrons are being shared between two atoms, oftentimes they're shared unequally. So remember we talked about a tug-of-war analogy. So it's sometimes that one atom can pull those electrons more strongly to itself than the opposing atom in the bond can pull back. So that's really referred to as this concept electronegativity. This is the ability of an atom in a molecule to attract electrons in a covalent bond. So the higher the electronegativity, the more strongly it attracts the electrons. Or you could say the higher the electronegativity, the more strong its pull. Okay, try to continue here. So this idea of electronegativity is, again, the ability of an atom to pull electrons to itself. And we separate out bonds into basically 3 types. One that we've already talked about, ionic bonds, where that pull essentially is so strong that the electron ends up on one of the two atoms in that ionic bond and has a negative charge to it, and then the other, essentially has lost that electron, so it has a positive charge. The other 2 types are known as polar covalent and nonpolar covalent. So these, again, are where electrons are being shared. In a polar covalent bond, they're being unequally shared. So in here, you see an X and a Y. So atom X, you can see, has you can see that Greek symbol above both the X and the Y. Those are to indicate that those have partial charges. So that Greek symbol just means partial. So you can see in the example here that X has a partial negative charge and Y has a partial positive charge. The one with a partial negative charge would have the higher electronegativity. That indicates that it can pull those electrons more strongly to itself, so it feels essentially an extra electron around it, and that's where it gets that partial negative charge. The Y would have the smaller electronegativity value, and so it feels like it has a partial positive charge on it. When there's no difference in electronegativity values between two compounds, say if they're the same, then that would be a nonpolar covalent molecule. So each of those electrons are being shared equally, and neither one of those atoms feels any partial charge to itself. Here's a listing of electronegativity values. These values will actually be given to you on the exam on your periodic table. So the periodic table that you'll have will have the symbol, the name, the atomic number, the atomic mass, and the electronegativity values for all of the atoms. So, and I'll post a sample copy of that soon, so you'll have that, be able to see what the periodic table you'll get on the exam looks like. Anyway, there is a trend for electronegativity, and that is that it increases from left to right across the period. It also decreases from top to bottom in a group. And you'll see that those in red are the ones with the highest electronegativity values, followed by the ones in orange that you see there. So the electronegativity value, again, is a representation of how strongly those atoms will pull electrons to themselves. It should make sense to you that, say, oxygen and fluorine and chlorine have high electronegativity values because they really would like to gain an electron. So instead of actually gaining one, they're just having it more closely to it in a covalent bond. And so that's why they have those high electronegativity values. In order to determine whether you have something that is a ionic bond, covalent bond, or polar covalent bond or nonpolar covalent bond, you can look at the difference in the electronegativity values. I'm not sure if I have a slide for that. So I'll just go back here. So typically what the general rule here, and I'll find it in your text as well. So on page 143, they give you the general sort of notes about this. So if you have bonds between atoms that have the same or similar electronegativity, they're essentially nonpolar covalent bonds. If you have bonds between atoms whose electronegativities differ by more than 2 units, then those are said to be ionic bonds, ionic compounds. Bonds between atoms where electronegativities differ by less than 2 units are polar covalent. And so that would tell you a little bit about the bond, and then you could use the electronegativity values to figure out which one is the partial negative charge and which one is the partial positive charge. The one with the higher electronegativity value will have the partial negative charge. The one with the lower electronegativity value would have the partial positive charge to it. Okay, so what you're looking at here is an electrostatic potential map on the right-hand side. This helps us look or visualize what the charge distribution is on a compound. So the red is the place of high electron density, blue is low electron density, and then there's a range of the colors in between. So here you're looking at sodium chloride. It's an ionic bond. That chlorine has that electron completely surrounding it, and so you can see it has that red color to it. Polar covalent bond, again, this is where the electronegativities differ. If you look up electronegativity values, you'll see that chlorine's is higher than hydrogen. So chlorine has a partial negative charge and hydrogen has a partial positive charge. You can see that also reflected in that electrostatic potential map where the red region is over that chlorine molecule and then the blue is over the hydrogen. Another note is that the bonds that we're talking about here are always a pair of electrons. So it's represented either by a line, as you see there, or by showing 2 dots for each of those electrons. In a little bit, I'll show you how to do those diagrams, and you'll be expected to know and understand that the line means 2 electrons, or to write it with just 2 dots. Here's one where there's a nonpolar covalent bond. Anytime you have two atoms connected together that are identical, then obviously there's no difference in their electronegativity values, so those are nonpolar compounds, and you can see that represented by the electrostatic potential map. Essentially, that charge is distributed equally over both atoms. Okay, so naming molecular compounds is a little bit different than, or is different than ionic compounds. Again, one of the things to be able to do right away when you're looking at a formula is you need to identify whether it's ionic or covalent. So you're looking for presence of a metal and a nonmetal to indicate ionic. You're looking for the presence of two nonmetals to indicate a covalent compound. If something has a polyatomic ion in it, then it's an ionic compound. So I should have mentioned that last chapter, but that's another thing to look out for. And because these nonmetals will combine with each other in different proportions, we use numerical prefixes to indicate in their names essentially how many atoms of each type are bonded together. So if you look at an example here, the formula N2O4, so there's 2 nitrogen atoms and 4 oxygen atoms combined together in this compound. And again, with molecular compounds, we're going to use prefixes to indicate how many atoms we have in a compound. So in this case, it's di-nitrogen, because there's 2 nitrogen atoms. Tetroxide, the tet refers to the 4 oxygens. Notice that the ending IDE remains the same, just as we had in ionic compounds. We use that IDE ending for the second element that's listed there. In terms of how you list them, the first element that's listed is usually more cation-like, so it's usually the one that would have a lesser electronegativity value. The second element is more anion-like, would have a higher electronegativity value, and again takes that IDE ending. So I don't have other examples here, but there certainly are more in your text in terms of naming, and I know I gave some on the pre-class assignment as well. Folks find this a little bit easier. It's just a matter of knowing the prefixes and using those appropriately. So I will say that if it's just one, so if that were, say, NO2, that would be nitrogen dioxide. So the ones are not included in the name. So if you just have one of a particular atom, it's just the name of that atom. We don't have, for example, mononitrogen. It's just listed as nitrogen. Okay, another skill for this chapter is to be able to draw electron dot structures, otherwise known as Lewis structures. These are relating and showing how an atom is bonded together, as well as all of the valence electrons that it has. So in order to draw electron dot structures, we use the symbol for the element and dots to represent the electrons. So here you can see a representation of a hydrogen molecule where those 2 electrons being shared in that hydrogen bond. If we take 2 fluorine atoms, again, if you recall, we can tell the number of valence electrons by the group number. So we look up fluorine and we see fluorine's in group 7, so we know that there's 7 valence electrons around an atom of fluorine. So that's how you can get the things on the left, and then when we combine them in a bond, you can see those 2 electrons shown in red being shared in a bond. Some terminology here: the electron pair that's in a bond is known as a bonding pair. All the other pairs that are surrounding those fluorine atoms are known as lone pairs. This does not mean a single electron. As the name implies, a lone pair means that pair of electrons, and they do exist that way. So this connects back to how they exist in orbitals, so keeping them together in 2s is important, because that's how they are occupying orbitals. And you can also see that the fluorine atoms themselves, if you look at each atom and count the number of electrons that are around it, including both of the red dots, you can see that each fluorine feels like it has 8 electrons around itself. And I'm going to use that word feels because it doesn't essentially have 8 electrons, but it does feel like that because it's sharing that electron with the fluorine atom that it's bonded to. Here's another way of showing, or just another example. So this is showing the formation of water using electron dot structures. Again, you can see that those single electron for each of the 2 hydrogens are in a bonding pair with 1 electron from the oxygen atom. So in water, there are 2 bonding pairs, one with each hydrogen atom and the oxygen atom in the middle, and 2 lone pairs. Here's some other examples. So here's showing O2 and N2. The O2 has a double bond between it, so there's two pairs of bonding pairs. Each of those could be represented by a line, and you can see there how we represent a double bond. The nitrogen has 3 electron pairs being shared between it, and so that represents a triple bond. This table is also given in your text. It gives you the bonding trends for elements that we're going to use. This is a good table to either memorize or write down. It gives you information about how many valence electrons from the group number, but it also tells you how many bonds each of those atoms in that group would be participating in. And that's important when you're trying to write the next part here, writing these structures for compounds. So, for example, boron in group 3 usually is involved in 3 bonds, and an example there of BH3. Carbon always wants 4 bonds, so there's an example of CH4, etc. So the noble gas elements do not bond with other atoms, so you'll see the number of bonds there listed as 0. So here are some electron dot structures of other compounds, so containing carbon and hydrogen, shown in both the electron dot with the dots shown, and then also just with the lines shown to represent the pairs. The best way to get used to this or practice with this is to just do a lot of these. So just given a few formulas, and there are plenty of examples in your book, to be able to write these out. And I'll give you the rules for doing that in just a moment. Elements, it's good to mention that those below the second row elements will sometimes have different configurations, and so they usually can accommodate more than just that octet around themselves. That obviously comes into play when we consider how to arrange them in structures. So I'll get back to that in just a little bit. Okay, so the steps here, and these are also in your text, so if you miss anything, they start on I thought they were in your text. Okay, well, I can't seem to find them at the moment, but they are here. So the first step is to find the total number of valence electrons for all the atoms in the molecule. So take each atom, including the number of each type of those atoms, and then compute the total number of valence electrons. Okay, trying a different location. Hopefully this will be a little quieter. So the first thing is to find the total number of valence electrons for all the atoms in the molecule, and then add an additional electron for each negative charge you have, or subtract one for each positive charge you have. So if you have an anion that has a -3 charge, you're going to add 3 electrons to the total. If you had, say, a cation that had a +2 charge, then you would subtract 2 electrons from the total. So that's the first step, is to calculate the total number of valence electrons in your compound. When you're done drawing your structure, you always need to go back and make sure that this matches, so that the total number of valence electrons that you calculated is represented in your structure. Step 2 is to connect the atoms. So we draw lines to represent bonds between the atoms. For hydrogen and second row atoms, we use the number of bonds that you see below. I mentioned this already before. For the third row and lower elements, they can often form more bonds than are predicted by the octet rule. Again, you still have to make sure that you're only representing the number of valence electrons that you have available. And usually the least electronegative atom is the central atom, so the one that you're going to put in the middle. Step 3 is to assign electrons to the terminal atoms. So after you have connected all of them, you count up the number of electrons that you have in those bonds that you've connected. Subtract that from the total, so subtract the number of electrons used for bonding from the total, and then complete each terminal atom's octet. So adding those electrons in pairs around the terminal atoms and completing their octet. And any of the lines count as 2, because those atoms are being shared. Essentially that atom feels like it has both of those electrons around it. I'll give you some examples in a little bit about this. And then the other thing to mention is that hydrogen only wants 2 electrons around itself. It's the one exception. So it just wants to be involved in one bond, and it will never have any other electrons surrounding it. Step 4 is to assign electrons to the central atom. So if you still have electrons remaining after step 3, you place them on the central atom. And then the last step, if you still have unassigned electrons remaining, but the central atom does not yet have an octet, you can use one or more lone pairs from a neighboring atom to form a multiple bond. And I'll show you an example of this when we go through a few of these examples. Okay, so here's the first one. Draw an electron dot structure for carbon tetrachloride. If you look up carbon is electronegativity is less than that of chlorine, so you're going to consider it the central atom. So you put carbon in the middle with chlorine all around. And again, carbon is one of those that likes to be in 4 bonds, so this makes sense. And so at this point, so step 1 is to calculate the number of valence electrons. So you look up carbon. Carbon's in group 4. It has 4 valence electrons. You look up chlorine. Chlorine's in group 7. There are 4 chlorine atoms in that compound, so you multiply 4 times 7. Add that up, you get a total of 32 valence electrons in that compound. When you're done with your structure, you need to make sure you have 32 valence electrons represented. If you don't, it's incorrect. So that is one main thing to make sure you always go back and check, is that the total number of valence electrons from step 1 is represented in your final structure, that you don't have more or less. Okay, step 2 is sort of arranging the atoms. So again, the carbon goes in the middle. It likes to be in 4 bonds, so bond it with each of those 4 chlorine atoms. At this point, you have 2, 4, 6, 8 electrons used. Step 3 is then putting electrons around the terminal atoms if you have electrons left, and you do. So you can see those are arranged so that each of those chlorine atoms has 8 electrons around itself. It has 2, 4, 6 electrons represented as lone pairs. It has 1 electron in that bonding pair, and then the other electron came from carbon. So it feels like it has 8 around it, even though one of those electrons is actually carbon's electron. And that's what we mean by using the octet rule here. Okay, so it does not mean that you have to have 8 of chlorine's atoms around itself, electrons around itself. It means that chlorine feels like it has 8 around itself. That includes that bonding pair. So as you're looking at each of the atoms, so what I typically do is say, look at chlorine and count how many electrons are around it. 2 in that bonding pair plus 4, 6, 8 in the lone pairs. So it obeys the octet rule. And if you look at the other 3 chlorine atoms, they also do. Okay, so that's step 3. The next step says to add up the total number of electrons that you have at this point. Oh, so 4 and 5 aren't shown here, but you would add up the total number of electrons that you have here at this point. So take a second to go ahead and do that. How many electrons are shown in the structure that you see there in step 3? Okay, hopefully you counted up 32. So there's 32 total valence electrons shown. So kind of the checks that you want to make to see if your structure is accurate is, do I have the total number of valence electrons needed? And the answer here would be yes. And then the next part, where possible, do each of the atoms obey the octet rule? Do they feel like they have 8 electrons around themselves? Each of the chlorine atoms do, and the carbon atom does as well. Notice that it has 4 bonding pairs, that equals 8 electrons. And so it also feels like it has 8 electrons around itself. So this is a complete structure. It is the best electron dot or Lewis structure for CCl4. So here's another example, H3O+. So again, the first step, total up the number of valence electrons. We have 3 hydrogen atoms. Each of those have 1 valence electron. Oxygen has 6 valence electrons. And then it has a +1 charge, so we know we have to subtract off an electron from the total. So we get 8. Step 2, we put oxygen in the middle. The reason we do that is hydrogen always goes around the outside. It can only be in 1 bond, So there's no possible way for it to be in the middle of a compound. That's just something that you sort of know as you go along. So hydrogens always go around the outside. So oxygen in the middle, hydrogens around the outside. Hydrogens are only going to be involved in one bond, so they're never bonded to two things, just one. And then each hydrogen is fine. Remember, hydrogen just wants 2 electrons, so you don't put any more electrons on hydrogen. In step 2, you've got 2, 4, 6 electrons represented, but you have 8 total. So now you want to add those 2 that are left to the central atom, the oxygen atom, and then check and see if this works. So oxygen, 2, 4, 6, 8, feels like it has an octet. The other thing that I haven't mentioned yet, which I should have, is the other thing that you should also check for is that each of your atoms obeys their valency. And what I mean by that is that the electrons that are around each atom are the same as the number of valence electrons that they have. So I'm going to go back to the previous example to show you that. So if you look at chlorine, chlorine is in group 7. So chlorine should have 7 electrons shown in its diagram, and you can see that. There's 6 in the lone pairs and then 1 in that bonding pair. So that's correct. And then carbon is in group 4, so your structure should show carbon with 4 valence electrons. And it does. It has 1 in each of those bonding pairs. If we do the same thing here for H3O+, hydrogen has 1 electron, 1 valence electron, and that's shown in each of those bonds. And then oxygen is in group 6, and if we look at the number of electrons that are around oxygen now, number of valence electrons, how many does oxygen have around it at this point? So oxygen's contributing 5 electrons in that compound, right? 1 in each of those 3 bonds plus that lone pair. Its valence is 6. Does this make sense? It does, because there's a positive charge on the compound. So the exception to obeying the valency for each atom is when you have charges, because essentially that's saying that that oxygen has lost that electron in this compound. So you do have to obey the valency rules for each atom and also take into account if there's been any gain or loss of electrons into that structure. And so this is a valid structure. It does make sense because we can see that that electron was lost from oxygen, and that's where that +1 charge came from. Here's another one, electron dot structure for CH2O. Carbon almost always wants to be in the middle, and it always wants to be in 4 bonds. So I can tell right away by looking at step 2 that that's not the end result here, but we'll follow through the steps so you can see. So again, step 1 is to calculate the total number of valence electrons. So carbon is in group 4, so there's 4. Each hydrogen has 1, so that's 2 times 1. And oxygen has 6. So we have a total of 12 valence electrons that we need to show in our structure. Step 2 is arranging the atoms. We put carbon in the center, hydrogen off of the carbon, oxygen off of the carbon as well. And so at this point, we have 6 electrons accounted for. So then we put the rest of the electrons around any terminal atoms. We can't put them on hydrogen, so we could put them on put them on oxygen. And you can see there in step 3, now we've got 2, 4, 6 around oxygen, 8, 10, 12 valence electrons shown. But now we need to consider the octet rule and also valency. So if we look at the figure in step 3, hydrogens are fine. Oxygen has 2, 4, 6, 8 around itself, so it's okay. But if you look at the number of electrons that oxygen has around it in terms of its valence electrons, it has 1, 2, 3, 4, 5, 6, 7, because it has 1 in that bond with carbon. Oxygen's valence is 6. So something's not right here. Plus, if you look at carbon, it only has 6 electrons that it feels around it. It isn't obeying the octet rule, nor is it obeying its valency. As written, it only has 3 electrons shown, and its valence is 4. So when you have situations like this, you have to consider multiple bonds. And we knew from before that carbon likes 4 bonds. We know it can't bond with hydrogen. So the only place it could have a multiple bond is with oxygen. So if we take that extra lone pair from oxygen and put it in a double bond, let's see what results. So if you look on the bottom right there. We'll take a look at that structure. So we have, let's just count up the number of electrons first, make sure we still have 12. Okay, so there's still 12 electrons. The hydrogens are fine. Let's take a look at carbon. Does carbon feel like it has 8 electrons around itself? Yes. So each of those bonding pairs, 2, 4, 6, 8. Does oxygen feel like it has an octet? 2, 4, 6, 8. Yes. Okay, so octet rule is being obeyed. And then the last check here is for valency. Look at the carbon atom. Does it, as shown, does it show 4 valence electrons in that structure? And it does, 1 in each of those 4 bonds that you see there. And oxygen has a valence of 6. Does that structure represent oxygen with a valence of 6? Yes, 2 in those lone pairs gives you, 2 lone pairs gives you 4, and then 1 in each of those bonding pairs gives you the 6. So this is a valid Lewis structure for this compound. What I haven't mentioned, they sort of are doing it here. Typically the dots are written in pairs, and they're written as if you had like a box around the symbol. So they're written kind of on the 2 sides and on the top, as opposed to just sort of written anywhere around the compound. That's just the traditional way of doing that. We mentioned before, or I mentioned before, that when you have atoms that are above the second and third rows, that often you end up with different arrangements. So let's take a look here. So here's SF6. Again, if you have a compound that has something with multiple numbers off of it, like 6 fluorine molecules, that's indicating to you that the S is in the middle, and not that there's sort of a long chain of fluorines then connected to the S. So in step 2, we put the S in the middle and fluorines all around. I skipped over step 1, but calculate the number of valence electrons. So we have 6 for sulfur, and then, wait a minute, sulfur, looks like maybe I made a mistake here. So sulfur's in group 6, so that's right. But we have 6 fluorine atoms, and that should say 6 times 7. 6 fluorine atoms times 7 would be 42, plus 6 would be 48. Okay, and they do have that represented in the compound, so that was just a typo. So that 4, at 4 there should be a 6. Anyway, in step 2 we arrange the atoms. You can see you've got 2, 4, 6, 8, 10, 12 electrons represented there in step 2. Then you put electrons on the terminal atoms to make 8. So you can see in step 3 you've got excuse me, 8 around each of the fluorine atoms. But if you look at the sulfur atom in the middle, it has 4, 6, 8, 10, 12 electrons around itself. This does happen in those higher atomic number elements. And we talked about this briefly last chapter, but here you're seeing more example of it. So this is okay. So if these are higher number atomic elements, it is okay for them to not obey the octet rule, and they often do not. So, and typically they have more than 8. There are some exceptions for less than 8, but the more common way that we see is more than 8. But the other thing to check here is valency, okay, and that is something that you should see all of these atoms obey. So if we look at fluorine, again, fluorine is in group 7, so it should have 7 valence electrons shown around it itself. And it does. Each of those fluorine atoms have 3 lone pairs, so that's 6. And then 1 electron that's in that bonding pair with sulfur, that's 7. So they're all correct. We look up sulfur. Sulfur's in group 6, and you see there are 6 bonds, so that represents the valency for sulfur. Each of those bonds has 1 electron that came from sulfur. So this is a correct Lewis structure for SF6. Again, those larger atomic numbers don't have to obey the octet rule, but all of the structures that you're doing have to obey their valency. So you should be expressing each atom showing the number of electrons according to its group number, as we've been going through with these problems. Here's another example, ICl3. So if we calculate the number of valence electrons here, 7 for iodine, 3 chlorine atoms each have 7, so we have 28 total. In step 2, we arrange the atoms, putting iodine in the middle. Step 3, we put electrons around those terminal atoms to make octets for each of those, and then see what we have left. And what we have left are 4 extra electrons. We put those on the iodine molecule in the middle. So I skipped through these kind of quickly because we've done a few, but let's take a look. So first, in step 4, count up and make sure we have 28 valence electrons that are shown. Okay, I see 28. And the next thing is, do each of the atoms feel like they have an octet around them? So chlorines do, iodine 2, 4, 6, 8, 10. Okay, so the iodine essentially has more around itself than you would expect. Whoops, sorry. But, and then the next step would be, are we showing valency for each of the correct atoms? And again, iodine is one of those that's in a lower group, so it's okay for it to have more than 8 around itself. So chlorine is in group 7, and it is shown with 7 valence electrons, so 6 in those lone pairs plus 1 in the bonding pair. Iodine is also in group 7, so you can see the 2 lone pairs, so that's 4, and then 1 in each of those bonding pairs makes 7. So again, this structure obeys the valency for all these compounds, and it's okay for iodine to have more than 8 around it because it's in one of those higher atomic number elements. Ozone. So O3, just arrange, so number of valence electrons here is 18. Arrange the oxygens in a chain. Step 3, put electrons around the terminal atoms, and then you'll see you still have ones left, so you put them on the central atom. But then when you take a look at that, you'll see, well, that the 2 atoms on the outside feel like they have 8, but the oxygen in the middle at step 4 feels like it has 2, 4, 6. And then if you consider valency, you've got 1, 2, 3, 4, 5, 6, 7 oxygen atoms around each of those terminal, the 2 oxygen atoms on the end. So there's something weird going on here. But we do have the right total number of valence electrons. So this is, again, another example where you have to consider multiple bonds. Can I put a multiple bond somewhere such that all of the atoms feel like they have 8 around them, and yet I'm still obeying valency for each atom? And you can see in step 5, a double bond between the first 2 oxygen atoms. Excuse me. First thing to do is to count up and make sure you still have 18 valence electrons. Okay, and you do. And then next, look and see, does each oxygen atom feel like it has 8 around itself? And I do see that. And then last, are each of those oxygen atoms obeying their valency? So oxygen is in group 6. So the first one on the left has 2 lone pairs, so that's 4. 1 in each of those bonds, and that makes 6. The central oxygen atom has a lone pair, that's 2. And then 1 in each of those pairs, so 3, 4, 5. Excuse me. And then the oxygen on the far right has 2, 4, 6, plus an extra 1, 7. Now, this is an example where those 2 oxygen atoms in the middle and on the right do not obey their valency. And this is an example where we would see something known as resonance in this structure. And what actually would happen with this compound is that double bond would resonate between the 2 oxygen atoms on the left and the 2 oxygen atoms on the right, so that all the oxygen atoms essentially felt the same number of electrons around themselves at any particular moment. And I don't know if that's coming up next here. Yes. Okay. So, so you can see here 2 different types of formulas below in the box. And if you look at each of them, they each have the 18 electrons total, okay, that we calculated here. They each have 8 around themselves, but they don't obey valency. And so when this happens, typically what we'll see is that resonance forms will exist, and that's okay. So how we represent that is a double-sided arrow that you see here. There's essentially two equivalent ways of showing ozone, the structure of ozone. You can see them in the box there. One is where the double bond is between the first oxygen on the left and the middle oxygen. And the next is between the middle oxygen and the one on the far right. And these are different arrangements. Okay, if you numbered the oxygen atoms, you'd see that they were different. But they actually resonate between the two, and they form what's known as a hybrid, which we won't get into much, but if you take organic chemistry with me, we'll talk a little bit more about that. These compounds turn out to be very important. Those types of structures that have resonance forms are much more stable than ones that don't, and so it affects their overall chemistry quite a bit. In terms of writing electron dot structures, either of these would be correct. Okay, so if I asked you to write the Lewis structure for ozone, either one here would be a correct form. And also to note that it does have resonance. And again, that's sort of brought out by looking at the fact that it's not obeying its valency rule. That's a clue that there's most likely some resonance, another resonance form. And you can have more than one. This shows just two resonance forms, but there are compounds where you can have three. Usually three is the highest, but sometimes you can have four resonance forms of each other. And again, notice the only difference between one form and the other is where the electrons are shown. So where those essentially move the double bond from one atom to another and move the lone pair as well. And that's all you do with resonance forms, is all you're doing are moving either lone pairs or bonds around a compound. Okay, so let's see what else I want to mention here. There are a lot of examples, more examples in your text of drawing structures. I recommend looking at those. Okay. The last bit here is calculating something known as formal charge. They're giving you a formula here. It's fine with me if you want to use this. I find it a lot easier to just think through the compound because I've already sort of led you up to that point with asking you to think about valency up until this point. So I'm going to skip through this slide. However, if this does help you in using this type of formula, feel free to do that. I'm going to show you a different way. Actually, I guess I'll have to show you using that same one. Okay. So if you sort of disregard the formulas here, just look at the compound, or actually I'll look back here. Let's look at these two resonance forms of ozone. And you would be asked the question to compute formal charges on each of the atoms in these compounds. A formal charge is taking into account those times when what's shown in the structure is not obeying its valency. So this is actually accounting for that and showing that. So let's take a look at the one on the left. Okay, if we wanted to assign formal charges for each of the atoms there. So look at the oxygen that's in red there, and see how many electrons are shown around it that belong to it. So what I mean by that is there are two lone pairs, right? The two pairs of red dots, so that's 4. And then 1 in each of those bonds, right? So 6. So that oxygen has, as shown, 6 valence electrons. That is the valency of oxygen. So the formal charge on that oxygen atom would be 0. Because the number of electrons shown around it is the same as its number of valence electrons. The next one in the middle. Look and see how many valence electrons are shown there. So there's 2 in that lone pair, 3, 4, 5, 1 in each of those bonding pairs. So as shown, it's shown having 5 valence electrons. Its valency is 6. So as shown, it looks like it's missing a valence electron. And because electrons are negatively charged, what do you think the formal charge on that oxygen atom would be? Did you say +1? It is +1. So The oxygen atom has, again, as shown, 5 valence electrons around it. I'm looking again at the one on the left, the resonance form on the left, the oxygen in the middle. So the formal charge on that oxygen atom would be +1 because it's missing an electron. Let's look at the atom on the far right in that same compound. Count out the number of electrons shown there, number of valence electrons shown there. 7, right? So it has 1 more than its valency. So the formal charge on that atom would be -1. Okay, so when you're computing formal charges, you're really just thinking about what are the number of valence electrons that are shown in the compound, and how does that differ from its actual valency? And using what you know about the charge of electrons to compute the formal charge. So the oxygen in the middle has a charge of +1. The oxygen on the end has a charge of -1, because the oxygen in the middle has 1 fewer electron than it should, and the oxygen on the end has 1 more electron than it should. There is no net charge in this compound, so all of your formal charges should add up to 0, and they do, +1, -1, and the other one was 0. Okay, take a minute to assign the formal charges to the resonance form on the right-hand side there, the one with the oxygen that's in green. Go ahead and assign formal charges to each of those oxygen atoms. Okay, so hopefully you have that oxygen on the left has a formal charge of -1, oxygen in the middle has a formal charge of +1, oxygen in the green on the far right has a formal charge of 0. Again, for the same reasons as before. The oxygen on the left has an extra valence electron shown, has 7 shown, so it has a charge of -1. The oxygen in the middle has 1 fewer electron shown, has 5 shown, should have 6, so it gets a charge of +1. You can use this way of calculating formal charges for any compound that you're given, any structure. Again, just looking up and seeing what its normal valency is and using that to figure out what's the change that's represented in the structure you're looking at, and then compute those charges accordingly. And again, it's shown here with that formula. Again, if you find this easier, by all means use it. I find for myself and for most students, just thinking it through and, again, using that valency example as a way to do this, it's a lot easier. This will also help you later when we talk about, say, oxidation numbers, just being able to know valency and know what that means and how it affects the overall charges on particular atoms. Okay, going to end here.